Our last presenter for this session is Guy Moore from the University of California at Berkeley. His field is material science and engineering, and he's done a practicum at Lawrence Livermore National Laboratory.
Thank you so much for the introduction. Thank you everyone for being here. Today I'll be talking about a ground-up computational approach to magnetic materials discovery using multi-scale computational approaches. There are many exciting applications of magnetic materials that are of interest to the Department of Energy, such as alternatives to rare earth magnets, which are both geopolitically and humanitarian problematic in that sense, and also spintronics, which provide an exciting alternative to conventional transistors, right? More efficient, possibly can also accommodate Moore's law, and magnetic cooling, magnetic refrigeration. You can actually use a solid-state magnet to cool surroundings that provides an environmentally friendly, possibly more efficient cooling source. So there are many challenges associated with magnetism, modeling magnetism at the atomic scale. A lot of us here are familiar with density functional theory. It's an approximation to the multi-body Schrodinger equation. And non-collinear magnetism, most magnets have some non-collinear component, so their spins don't lie along a common axis. But non-collinear DFT is much more computationally expensive, and actually optimizing and finding the magnetic ground state is a very large dimensional optimization problem. And finally, DFT is fundamentally 0 Kelvin. So how do we extend our models from DFT to finite temperatures and possibly accommodate for hysteresis effects? So how do we tackle this problem? I propose and have developed each level of a multi-scale computational approach that wouldn't have been possible without the support of CSGF and the greater community and the practicum experience. So I'll try to cover everything from atomistic DFT up to the lattice models, Monte Carlo results, how do we get finite temperature behavior, and finally, even the continuum. So I'll start from DFT and calculating U and J parameters, which I'll talk a little bit about, as well as a new exchange correlation functional, which we've implemented in VASP source code, but we hope to extend to other open source codes. VASP is not open source, but our code patch will be. So U and J values parameterize the on-site Coulombic exchange that accounts for self-interaction errors that we actually have in DFT. So self-interaction errors arise from neglected multi-body effects that we neglect in DFT that we would have in the Schrodinger equation. And we actually calculate these U values in a self-contained fashion within DFT instead of spitting to experiment. So it's fully predictive, and we're able to calculate. We performed a high throughput study where we calculated the distribution of these U and J values across the periodic table. Because people usually use one U value for all elements, so we're showing that we need to be a little bit more careful in how we choose U and J, especially for magnetism, where U and J values have a very strong effect on the magnetic ground state, especially J values, which actually incorporate the exchange between electrons of different spin. So in VASP source code, fully open ACC and MPI parallelized, using three-dimensional fast Fourier transforms, so generalizable to other plane wave basis codes, DFT codes. We actually compute this source-free functional. So if you've ever accidentally broken a magnet, you notice you never have one north or one south, right? I've done this many times, sometimes on accident, sometimes intentionally, but you always have smaller magnets. And this is a fundamental property of magnetism from magnetostatics. And so essentially we see that by removing monopoles in a unique fashion using the Helmholtz decomposition, we get a much more symmetric on the left, much more symmetric looking magnetic field lines. And we actually converge much better to the magnetic ground state compared to conventional GGA, where you see these monopoles are actually forming between atoms. And I mentioned convergence. So we can actually, for this other oxide system, if we perturb the moments from their symmetric ground state and actually look at convergence, we see that for source-free, the algorithm, the DFT, converges much more rapidly to the ground state energy convergence. We see the movements move from their broken symmetry perspective to their symmetric ground state as established experimentally using neutron diffraction. Whereas for conventional non-collinear GGA, the moments don't move very significantly. And this is based on the work of Sangeeta Sharma at the Max Planck, one of the Max Planck Institutes, which I showed on a previous slide. But we've actually implemented this in a plane wave code. So I've talked a little bit about local convergence and improving local convergence with this new exchange correlation functional. Now I'd like to talk about global convergence. So we've actually developed a hybrid algorithm, and this is developed in an open source workflow that calls DFT under the hood, but we actually created a hybrid algorithm that incorporates atomistic spin dynamics, physically inspired, with particle swarm optimization. And via this technique, which is inspired by some other studies, but no one has connected these two different algorithms, as far as I'm aware, and we actually achieve global convergence to the magnetic ground state for a representative test set of different magnetic systems across different chemistries. So this is actually a stochastic neighbor embedding, projected the high dimensional landscape onto a lower dimensional surface, and we see that we actually are able to get out of local minima to the global minimum, which is what particle swarm optimization, agent-based optimization techniques are known for. And we actually converge, again, for another test material, we converge to the experimentally resolved ground state. So this is non-collinear, as in the moments are canted out of their collinear configuration. And we converge rather rapidly within 20 to 30 iterations. Okay, now I'd like to move up one level of spatial hierarchy and actually look at lattice models. So a simplified picture of magnetism where you have spins interacting on a lattice. Using a custom Cython Monte Carlo code optimized using MPI, parallel tempering, and OpenMP for Metropolis updates, we get reasonable agreement with experimentally resolved transition temperatures. And these are from exchange constants from DFT, so ab initio computed exchange constants. We also see agreement with the change in entropy associated with the phase transformation, which people care about for magnetocalorics. Essentially, it governs your cooling power. And we see at the critical temperature, it agrees rather nicely with this Spinel test set at different endpoints of composition space. And this is using a mean field model, again, informed by density functional theory. I'm going to move up one more length scale to continuum and actually talk a little bit about my practicum, which is an essential part of the DOE CSGF fellowship, as we all know. And I think this was a really wonderful opportunity so I worked under the mentorship of Dr. Tae-Wook Ho, and actually he mentored me through developing a phase field code from scratch that we hope to make open source. Again, this isn't Cython, but it's fully parallelized. It's a spectral solver using three-dimensional FFTs. And so Dr. Ho cares about structural phase transformations. So FCC to BCC, and this is at Livermore. So FCC to BCC structural transformation where your crystal is actually changing. We're actually able to look at how the dynamics and nucleation of these variants occur in a material, and their nucleation across grain boundaries. So, and at HCP to FCC, you see this threefold symmetry due to the hexagonal symmetry of the underlying crystal lattice. We can generalize this to other phase transitions. So also looking in the collaboration with Sinead Griffin at Lawrence Berkeley National Lab, actually informing from DFT studies that have happened years ago. But again, this is in our custom phase field code where it's a multiferroic, so you have structural order parameter distortions of polyhedral connected to polarization, as shown in the middle figure. And we incorporate a grain structure and apply a compressive stress to the material. And this actually agrees with experiment. We get these finger-like patterns occurring as a result of the misfit strain occurring at these grain boundaries. So this was reassuring, and if people are curious and see experimental data, happy to show you as well. we're working in collaboration with the experimentalist who's been able to resolve these structures, which I'll talk about at the end. But essentially now connecting this to magnetism. So my practicum actually informed my thesis in a nice way, where you can actually, there's a lot of nice statistical mechanical machinery to go from the lattice model using Gaussian integral transformations, Hubbard-Stratonovich transformation for some of the field theorists out there. We can actually get a Ginzburg-Landau functional, including gradient contributions. And we can actually look at a new time evolution equation with precession, which is the first term on the left, which can be rigorously derived from quantum mechanics. The second term is more phenomenological, but we inform it with the double well potential, so from this Gaussian integral Ginzburg-Landau for energy functional. And what this allows is it actually allows for the magnetization to change magnitude across the phase transformation. So as we see on the right here, this is actually the dynamics of the spins. Again, using this semi-implicit spectral solver, we look at the dynamics, and we can actually cycle under applied field and applied field and temperature, where the area between those two curves is indicative of the cooling power for a magnetocaloric device, so for a magnetic refrigerator, getting back to that application. So in conclusion, I've talked about the problem, the multi-scale problem, hysteresis, which is fundamentally non-equilibrium. We must include dynamics to incorporate multiple sources of hysteresis at different length scales, non-collinear magnetism, complex optimization problem, and how do we inform continuum models from ab initio-informed data or energetics. And we address these challenges using a holistic approach that incorporates the physics at multiple length scales based in rigorous statistical mechanics, which we've extended to ferrimagnets, antiferromagnets. If people are curious, please ask me afterwards. Happy to get into the nitty-gritty physics and math details. So in conclusion, I'd just like to thank my advisor, my mentors, and most of all, possibly, is the CSGF fellowship and the community, and also my mentors in undergrad who encouraged me to apply for CSGF. And without this source of funding in the greater community, I wouldn't be able to achieve this research. So thank you once again for attending my talk. Please stick around for the other talks. There's wonderful talks later today and obviously earlier today, and the rest of the week. So thank you.